So this next presentation or session is on, again, opportunities and challenges for machine learning in the African electricity sector. And we're going to hear from three really awesome speakers. So in order, Bhekisipho Twala is the Executive Dean of the Faculty of Engineering and Built Environment and Professor in Artificial Intelligence at Data Science at the Durban University of Technology in South Africa. Next presentation will be from Simone Fobi, who's a PhD student in mechanical engineering in the Quadracci Sustainable Engineering Lab at Columbia University in the United States. Previously, she was a research scientist at IBM Research in Kenya. And then the last presentation today will be from Nathan Williams, who is an assistant professor at the Golisano Institute of Sustainability at Rochester Institute of Technology in the United States. And previously, he was an assistant research professor at Carnegie Mellon University, Africa, in Rwanda. So we'll start with the presentations from the three of them, and then open it up for Q&A. So Bhekisipho, are you able to share your screen? And you'll be the first.
Can you hear me?
Yes.
Okay. I've been having problems, but I'll just go through it, but I can always post it to, email it to people if they're interested in my talk.
Sounds good.
Yeah. So I'll just go through it, but anyone who's interested, you can forward them my email, forward me their email addresses, and I can be able to email it to them. Anyway, the issue of climate change and using machine learning methods has been quite an interesting one in the context of Africa, because not only machine learning was it going to help in terms of dealing with climate change, it was also going to help African countries improve. I mean, you know that currently we've got, everybody can hear me?
We can hear you.
Okay. So what happened is, so that has been quite an issue as well. One aspect of it that I've picked up is that we always, in machine learning, we always, we predict things. For example, you can predict now that climate change impact in 20 years will be A. But we never, once we reach point A, we don't have mechanisms to go back to our initial prediction point, whereby you can able to tell that this was the prediction that was made, for example, in 2010, and here are we now in 2020. Instead, we keep on continuing with the predictions without having to look back. So that's one thing that prediction has always been a problem in terms of climate change, not even in other aspects of it as well. When you look at it also in another scope, is that in Africa, we have problems of machine learning is sort of like IT intensive. I mean, you need your IT infrastructure to be in place. So as you know, in Africa, we lack a proper sort of like sound or efficient IT infrastructure. So that has been our problems in the past, whereby all these ideas are there, but we don't have a much more sound IT infrastructure. Machine learning requires that, because you'll be sort of like looking at massive data sets. And also from the data set side of things, we don't seem to have repositories or databases that can handle massive data sets. Remember, when you develop a system, you need data sets that are much more of good quality. So in Africa, not only is our IT infrastructure a bit dodgy, also the data kind of like is not of good quality because of the systems that we have in place. As a result, most of the research that we do is research that is based on data from the first world, because the first world has got open data. You can able to access it and come up with all these methods that you can use in terms of climate kind of like change. One reason that I've seen regarding that is that we don't market ourselves well in Africa. By saying that, I mean, I always travel abroad, and whenever I go abroad, I hardly see anything about Africa on the TVs. And also, when I go abroad, I hardly go back and check as to what's happening in Africa. I'm always focusing on developing countries. So developed countries. So as a result, I always say to my colleagues that we should market Africa well. We should be able to talk about things that are happening in Africa so that people know as to what's happening in Africa. And that opens the doors for collaboration, effective collaboration as well. So those are things that that have been sort of like holding us back in terms of doing much more sound research in machine learning and climate change. The first one is the data issues. The second one is the IT infrastructure. And the third one, which is also critical, the skills. We don't have the right skills in Africa. They're limited. People have done machine learning in Africa. You can actually count them. Whereas when you compare that to the first world, there's a critical mass of people who are working on machine learning and they're applying it in different fields, including kind of like climate change. So that's where we've been lacking a lot as well, that because our universities as well, they tend not to offer modules in machine learning or big data analytics or smart cities, Internet of Things from undergraduate level. Instead, most of the research that we do is already at postgraduate level, whereby someone is focusing on a particular topic, but that topic might not cover the whole spectrum of sort of like machine learning and climate change. So those are the things that my slide was focusing on, as to, in as much as the ideas are there, we see the benefits of using machine learning in climate change in all sorts of aspects and its impact as well. We seem to be lacking in sort of like a certain kind of like aspect of things, because as Africa, we sort of like lagging behind compared to other continents or the developed world. So that's the things that I was going to cover up in my slides, but I'm going to send the slides as well, because I touched upon quite a number of things as well as to how we could improve. As a way forward now, in summary of my talk, I did talk about maybe it's high time that in our schools, we don't teach, for example, physics like as an isolated subject. During our time, that was fine, but maybe now it's time to mix things up, make it more sort of like multidisciplinary. Someone who's done physics can do maths, can do other modules, psychology, social, sort of sociology and stuff like that. Or then that will be kind of like great. Same with mathematics. It shouldn't be taught in isolation, and other subjects as well. So that's from the lecturers or the teacher side of things. Then, because we always say, there's always this saying in Africa that the students are not good enough. There's always this saying that our education systems are not good enough as well. So, but I always pose the question, but what are we doing as well as teachers and sort of like lecturers? So for me, that's a good step, that when we teach, we should introduce new methods, flip room, classroom things and stuff like that, so that our students are able to sort of like grasp things as well. That's from the teaching side of things. From the student side of things as well, I think they should utilize the advanced technologies that are out there now. Most of the students now, they've got cell phones, they've got a lot of things, but if they could utilize it in terms of improving their knowledge and understanding things, that will be quite kind of like useful as well. Then I always target parents as well. We tend to focus more on teachers and the students. But as parents, I always ask parents from time to time, who teaches your son or your daughter mathematics? Then they just look at me. And I said, but you expect your child to do well in mathematics, but you don't even know who's teaching your child mathematics. So I blame parents as well, to say, parents, it's high time you get involved as well. So that the three, students, teachers, and parents, we come together. Then we come up with a very good system that will make students sort of like understand as well. So for me, that's the way forward. I mean, I know that machine learning has got its critics as well, especially on the AI side of things, whereby they talk about jobs and stuff like that. I mean, that's a topic for another day, but it's something that you always have to keep at the back of your mind. It has had its successes, machine learning as well, in different kind of like fields. So in terms of moving forward, I think we should utilize it. It's only that it doesn't accommodate mediocrity. It has to, you have to raise the bar. Students should be able to understand, they should be able to program, their maths has to be up to scratch, their statistics, their psychology, their philosophy, different fields. That's what I like about machine learning. And if you're looking at it in the climate change context, it's very multidisciplinary. So maybe from moving on, we should now come up with modules, even at schools or programs that are multidisciplinary. Gone are the days when I was an electrical engineer, I was focusing on electrical engineering. But you need a psychologist on the side. You need an econometrician on the side. You need a sociologist, a philosopher. So we should come together with those problems. So moving on, we should be trying to do that. And we should be able to crack this problem of climate change and using machine learning. So that's the summary of my talk.
Wonderful. Thank you so much for sharing those that taxonomy and general considerations for doing work in this area. As mentioned, we will be sure to share the slides with those in attendance afterwards. So we'll kind of have questions at the end of all three of the presentations, but for those in the audience, please feel free to start dropping questions in the chat even as of now. So our next presentation will be from Simone Fobi. Simone, are you able to unmute and share your screen?
Yes, actually, I think Nathan will go first before I do. He's confirmed that he'll present right now.
Okay, sure. We can have Nathan go first, no problem.
Sure, can you hear me?
Yes.
Great, let me get my slides shared here. And this was sort of unplanned, but Simone and I actually work on the same project, so I didn't know she was joining this until last week. So we tried to coordinate a little bit here. Give me a second. Awesome. All right, can everybody see my screen here? Is that working properly? Or am I sharing the wrong screen, I think?
We can hear you fine.
Okay, hold on.
And see your screen, or we could.
Good, all right, got it. All right, great. Okay, so yeah, I'm Nathan Williams. I work at the Gonzalo Institute for Sustainability at the Rochester Institute of Technology. I'm also the executive director of the EGuide Initiative, and that's going to be the theme of my presentation here. Just quickly, so my plan is to give a quick introduction to EGuide, what we're about, some of the work that we're doing, particularly as it relates to machine learning in the electricity sector in Africa, and then talk a bit about opportunities and challenges that I see in the sector. I'll echo a lot of what Bhekisipho said, but hopefully that sets us up for a good discussion. So the EGuide Initiative was launched in January 2019. This is the Electricity Growth and Use in Developing Economies Initiative. We are supported generously by the Rockefeller Foundation. This is a multi-university collaboration. So the high-level focus of EGuide is using data to improve the planning and operation of the electricity sector in developing countries in general. We have a focus in particular on East Africa. We also have a project in Nigeria, but really focusing in on the demand side of the power sector. And it's our view that we've invested a lot in trying to understand the supply side of the power sector. Not enough has been done on the demand side, which really drives the way we plan the supply system. And there's a lot of opportunities, I think, here for machine learning and trying to understand behavior, predict consumption for electricity, for example. So our focus areas are using data to make better predictions of electricity consumption. This is a huge challenge for the sector. Simone's going to talk about this, so I'm not going to upstage her. I will leave the details to her. We're also doing some work trying to sort of develop methods to co-plan electricity and agricultural infrastructure, sort of taking into account the interdependence of these two sectors. And then using these data that we're generating to improve planning and system operation. And as well, we have another project focused on mapping power quality and reliability using night lights imagery. And so, like I said, this is a multi-university collaboration. There's myself at RIT, Vijay Modi at Columbia University, Paulina Jaramillo and Barry Ron at Carnegie Mellon, Jay Tanej at UMass, and Chris Elvidge at the Colorado School of Mines that are really driving this work. So I'm just going to do some brief summaries of projects here. I know I'm supposed to stick to 8 minutes. I'll do my best. So one of the projects, and Simone is going to dive deeper into this because she's really driving this, but uncertainty around electricity consumption and how that consumption grows over time is a huge challenge. It leads to inefficient allocation of resources, high costs of energy, and poor planning in general. Perhaps in the discussion we can talk some details about this, but the idea here is that we do have sophisticated energy planning tools, but these really rely on the quality of data going into these models. And so really what we see as sort of the weak link in that chain is the poor quality of demand data that's available. Oftentimes it's just broad assumptions that go into these models. And so we've been doing work partnering with utilities, taking hundreds of thousands, data from hundreds of thousands of geolocated customers with historical billing data, and trying to apply deep learning to make large scale prediction at a fine spatial resolution that we can use to then help these system planners plan their system in a more efficient way. And then I also have some work going on in the off-grid sector, again, focusing on demand prediction. Here we have a much smaller sample, and this is a challenge that I'll talk about, just the quantity of data available. But we have sort of a richer data set, and again, using machine learning here to make predictions about electricity consumption growth, which helps us to size those systems properly, as well as to plan those systems from a financial perspective. Bankability of these problems is a huge challenge because there's uncertainty around revenues, and if we can make better predictions about consumption and revenues, this helps make the business models for these off-grid companies more viable. We're also, have a few projects looking at how we can use consumption data that we're generating to improve planning and operations of power systems. These are just a couple of examples. One project is looking at trying to estimate, what are the subsidies that are actually flowing towards grid extended customers. There's a perception that off-grid is much more expensive than on-grid. The price per unit that customers pay is certainly a lot less expensive, but typically those connections make huge losses. And so what we've found typically is that in Kenya, the data we're working with, each new connection on the grid loses maybe $1,200 to $1,300 over its lifetime. And so we're trying to understand, what are those subsidies? Who are they flowing to? How do they compare with alternatives? And what does that mean for sort of efficient allocation of resources for electricity access? We're also looking at data on small commercial customers, trying to understand how that grows. How do sort of local population distribution patterns affect consumption? Is there complementarity between infrastructure systems and services that enable productive use of power? These are some of the things we're looking at. And then on the sort of electricity agriculture side, really recognizing the fact that, 54%, I think, are the statistics of sub-Saharan Africans work in agriculture for their primary livelihood, and yet productivity remains low. Our consumption modeling work is focused on making predictions based on historical data. But what that historical data tells us is that when people are connected, they use very little power. There seem to be barriers to using that electricity for productive use or for sort of developmental purposes. And so what we're trying to do here is develop methods using data to help sort of cross-sectoral planning, in particular between electricity and agriculture, to improve the efficiency of those investments, to make sure that that electricity is not just powering light bulbs and cell phones, but also irrigation and agro-processing applications. So the goal here is to develop some geospatial data products to facilitate that cross-sectoral planning. And then Yeah, so this is from India. So our colleagues at the Colorado School of Mines are doing work with night lights data. And effectively what they're doing is trying to measure power system reliability and quality using these night lights images. And so here, what we see is, so the color coding here tells us when power was available in these different regions. So the white areas have more reliable power. The red regions had power sort of in, what is this, November 2015. In any case, the idea here is to develop a data set that allows us to sort of measure infrastructure and the quality of that infrastructure. And this feeds back into the consumption predictions work because, of course, the availability of power is a big determinant of how much electricity people can actually use. So that's high level what we're working on at EGuide. I know that was very quick. On the opportunities, I think there are opportunities to help sort of fill data gaps using publicly available data. So, if we have a large data set, for example, in Kenya, that we can use to develop a predictive model, can we apply that in the country with less data, right? Now, there's questions about how generalizable those models are. Simone's going to talk about this. But, can we use publicly available data to sort of fill data gaps? Measuring infrastructure, it's maybe surprising, but a lot of utilities on the continent don't actually know where their infrastructure is. So where is infrastructure? Where are the power lines? Where has electricity already been extended? We have colleagues at UMass in EGuide that are looking at, can we measure road quality, for example, using satellite imagery? How reliable is it? Coming back to the power system reliability work that I just spoke about. And then how can we use these data to improve planning, design, and sort of efficiency of electricity systems using these data? I think there's also opportunities to identify productive use applications. We have some work going on trying to use pollution signals in satellite imagery to identify where small-scale irrigation is already happening, for example. And hopefully with that information, we can identify other opportunities for productive use. And then the off-grid sector, solar home systems in particular, are doing interesting work, essentially using the data they collect on their customers and with machine learning to create credit models for unbanked populations. So helping people access financial services. So there's a lot of interesting applications. The challenge is data. Data is huge, as Bhekisipho said. So data availability, oftentimes it's not available at all. Sometimes the quality is poor. And even if the data exists and is good quality, how do you access it, right? One of the challenges is just knowing whether it exists or not. It's not as if there's a public database that you can access. So does it exist? Where is it? Who has it? And even within utilities, we've found, they often don't really know what data they're sitting on or where it is. And we've invested a lot of time and energy just trying to build the relationships necessary to locate and access data. So that's a huge challenge. And as Bhekisipho said, capacity, skills, and infrastructure for data gathering organizations is also a challenge. A lot of our partners aren't necessarily experienced in this area. And I've invested a lot of time, with partners, helping them improve their data collection methods and infrastructure, as well as sort of data analysis skills. One of my partners was sitting on millions of lines of smart meter reading data, and they were analyzing in Excel, which was just painful. So capacity is a huge challenge. Data standardization as well, particularly in the off-grid sector. Everybody's collecting different data, which makes it difficult to sort of build standard tools, machine learning tools that apply across geographies and companies. So there's a lack of standardization in what data is collected and how it's collected. And of course, we also have to think about privacy and data security as well. So my closing thought will be that there's huge potential for data and machine learning in the sector, but capacity building is going to be crucial. We can't do machine learning without high quality data. So this requires organizations that are able to collect, organize, store, and work with these types of data. Just as a note, if there's anybody out there that's interested, EGuide has a couple of capacity building initiatives in this space. As was mentioned, I formerly worked at Carnegie Mellon University, Africa, which is a fantastic organization based in Kigali, Rwanda. We have programs on information technology, electrical and computer engineering. I believe they're developing a machine learning master's as well. We do have support for companies that want to hire interns from the campus in the electricity sector. So if anybody's interested in that, please reach out. We have fantastic students. Or I say we, I still feel attached to the campus. And we also have a program that sponsors mid-career professionals from Africa to complete the African Leadership University's Africa Industrial Internet Program, which is focused on building data science skills and capacity. So human capacity is certainly, I think, the biggest challenge. So I'll leave it there. And I apologize for going too long.
No problem, Nathan. Thank you so much. That was a great talk. And so I guess we'll hand it off to Simone before opening it up for questions. Again, if you're in the audience, feel free to drop questions in the chat and let us know also whether you'd like to ask them yourself or be unmuted. And Nathan, one of the participants, says that they are glad you went too long. So there we go.
Great.
Yeah, so Simone, take it away.
Can everyone see my screen?
Yes.
Oh,
Now we can see it.
okay, sounds good. Hi everyone, thanks again for having me, and sure, let's get started. So my work has mainly been focused on electricity planning in developing economies, and that covers a lot of African countries. And so when we talk about residential electricity planning, we're really trying to ask the question around how do we increase the fraction or the percentage of the population that has access to electricity? How do we increase that? And to be able to do that, there are a few things that arise. One of them is around what is the most cost-effective technology to be able to do that. And the cost-effective technology question comes up because now there are quite a number of interesting technologies to consider. We have solar home systems, we have mini grids, we have the existing grid, which maybe in more industrialized regions when they were doing electrification, those technology choices weren't necessarily cost effective. So if we look at the figure, for example, that I present on the right here, I show a few technology options: solar home systems, mini grids, and here I'm really trying to quantify what the value of each service is to a consumer. In the figure on the horizontal axis, I show some consumption in kilowatt hours per month. And I show a tariff on the vertical axis, which captures the unit cost of electricity on a given system. So if we take, for example, a solar home system, small panel, where the unit price of electricity is around $3 per kilowatt hour, that system might be able to support a small amount of demand, which is maybe about, let's say, 1 kilowatt hour. As we move towards mini grids, where the tariff drops significantly to about 50 cents, and the amount of demand that that system can support, it's a lot more, meaning that you can have more appliances, you can move away from just a couple of lights. And then finally, when you offer grid service to someone, they're paying about 10 cents per kilowatt hour, and that system can support as much as you can put on it. So to a consumer, there's really an incentive to want to move towards grid services, just because the cost per unit of electricity is lower. However, in a lot of, at least the countries that I've looked at, let's say Kenya, for example, to be able to make that grid connection or offer that grid service to someone, it costs the utility about $1,000 per connection. So if that connection is made, if that grid connection is made and the demand is very small, it becomes very difficult for the provider of electricity to remain financially viable, and while still increasing the number of people that have access to electricity. So there's sort of a balance that has to be made in terms of matching both the technology to the right consumer based off of what they would consume prior to offering a connection. So to do that, you have to be able to estimate what someone would potentially consume once they receive an electricity connection. So a lot of my work asked that question. A lot of the work in EGuide asked the question on, and Nathan did mention it, how do we estimate demand? Because that's not really as explored as the supply side question. Another consideration, when I just wanted to show this, is when we think about electricity planning or electrification plans for a lot of African countries, we leverage some existing planning tools. Here I show on the right an output from well-known models called Network Planner that made a plan for a region in Senegal. And it shows some proposed technologies relative to the existing grid. Each dot here represents a population center, and the size of the dot is the number of people in that center. So larger dots means more people there and indicating also more demand. So I just wanted to bring this up to make a key point that if we look at this point in the red box, that's a point of considerable demand, and that point is proposed to be electrified through connecting it with the existing grid. And that's because that point is, one, connected to other or close to other points that have considerable demand, and two, it's relatively close to the existing grid. If we look at another point of similar demand that's further away from the existing grid, but also surrounded by points of smaller demand, that this point in the red box gets proposed to be connected via, say, solar PV. So for us to be able, sorry, the point I'm trying to make here is that your electrification plan actually changes both based off of what your demand is, but also where your demand is located. So when we really think about access planning, we're trying to figure out where would the demand be, and can we anticipate what the demand would be so that we can propose the right technology. So in general, I'd say demand estimation is probably the central theme of our work, and that's sort of what I'll focus on for the rest of this presentation. So the objective, given at least that motivation, is quite simple. Given some series of households, we want to be able to say something about what their demand would be, their electricity demand would be, either predict a consumption class for the demand or an actual kilowatt hour value. But whatever approach we settle on has to meet some criteria. One is the approach has to be scalable. We need to be able to apply it to countries, like it has to work countrywide. And when we move to regions that are now trying to increase their electrification rate, that the approach has to be transferable. So we want to be able to learn from places that have been or are more advanced in the electrification process and apply what we've learned to places that are now starting to electrify more of their population. Okay. So to do demand prediction, we've considered some data to support that, one of them being satellite images, mainly because satellite images have good global coverage, good resolution, and so they make it, or they make sense for scalability. We've also considered merging satellite images with other data sets from surveys and nighttime lights, and there's quite some work that still needs to be done on how do you appropriately find relevant data sets and how to merge them. But ultimately, once we have images, some auxiliary data, we want to infer something about electricity consumption, what we would see in a meter. And so far, the approach we've been taking has been supported by data provided by Kenya Power. We have about 135,000 postpaid residential customers. That might seem sizable, but it's only about 3% of their residential customers. So it's just really a small sampling of customers there. And we have their billing data for 2010 to 2015. In general, the approaches we've taken are just presenting a building of known consumption in an image, and then some surrounding pixels for context. And like I mentioned before, we want to be able to infer something either about a demand class for the image or the building in the image, or some actual kilowatt hour consumption for the building in the image. And then later on, tie that back to the electrification planning process, which I had mentioned before. So here, I'll just briefly present one of our results. So in the context of the technologies that we've mentioned. So one of them was a solar home system. And if we want to be able to identify customers who might benefit from solar home systems, we might create some thresholds in the data, saying, for example, one class might be less than, on average, 25 kilowatt hours per month. And then another class might be greater than 40 kilowatt hours on average per month. That might be one model. Another way to think about it is if we want to find people who the utility cannot afford to miss, or who the utility must connect, we can create a different thresholding approach where one class might be less than 90 kilowatt hours and another class might be greater than 100 kilowatt hours. So this is just to be able to show that we can directly tie the modeling with the applications to electricity planning. And when we actually train a model using some of these approaches, we see that satellite images are quite valuable in learning something about the electricity demand of individual buildings. So here, when I present B1, B2 models, it's just relative to the models shown for solar home grid. And we can also ask the question, how do these models perform across different consumption bins? So here we just reported for the two classes, but we've actually taken a continuous problem and have made it binaries. So how do these models perform across different ranges of consumptions or different bins of consumptions within these classes? When we do that, we notice that the models seem to learn, both of them seem to learn around the edges, which is good, but they start to struggle in the middle band, which is people who are around, let's say 40 to 80. And one, that suggests that there might be some opportunities to redetermine what the consumption bins are. However, we have to balance those considerations with what is relevant to business models or utilities who would be making decisions for connection. So we can't always optimize for where does a model do best. It also has to be, we need to find the relevant set of customers. So there's a bit of that balance that needs to be achieved. Another thing that we've sort of looked at are how valuable are satellite images when we think of electricity demand in African countries. Are satellite images actually able to measure or identify relevant features that correlate with electricity demand? To do that, we took an approach using CycleGAN, where we take images from places that have, say, low electricity consumers and try to generate the same, generate a new image of the same area as though it had high electricity consumers. And vice versa. So I'll show you an example of what I mean here. Let's start here. So on the leftmost column, these are just some sample images of places that had on average low electricity consumers, and we generated, or tried at least to generate a fake image as such that that image will get classified as having high electricity consumers. Now, when we do the difference of both images, we can identify what was added or removed from the image, and that starts to suggest to us what is relevant or at least correlated with electricity demand. We also do the reverse, which is take an image with on average high electricity consumers and try to go in the opposite direction. To us, what was interesting here was that roads and buildings seemed to be the most relevant features, but we also noticed that there was a tendency to make things more, if I may say, agricultural when we moved from high to low. So we noticed that in addition to roads and buildings being important, there's also some influence of urbanization that is embedded into it, which suggests to us that there's opportunities for work around measuring urbanization levels that are correlated with electricity demand. So this just here at least highlights some of the things we've done. I think probably what is more interesting is specifically talking about what are some opportunities or challenges there. So I mentioned initially that we want to be able to predict the electricity demand of a household, but how do you define a household? So here's a satellite image with a few structures in the image and a red circle around the images. In a lot of African, at least sub-Saharan African countries, in the rural areas, households might own multiple structures. So when you look at an image, how do you determine which structures belong to the same household? And if you're coupling that with data from meter, then it's a bit harder to be able to pull apart how do you aggregate the structures to match a household? So that's one challenge that we're observing. The other thing is also when you look at images, not every structure is a household or has people actively living in it as their home. It could be industrial, it could be small commercial. Industrial is slightly easier to identify, but if you're trying to differentiate between a shop and a house, or a house that might have a shop in it, it becomes harder to separate both of them just by looking at images alone. So those are some of the things that we are noticing as we undertake this process. Another issue that has been brought up a lot through the other talks is data quality. We're also observing that. For example, just looking again at this image, if we're focused on just structures, we want to be able to specify the structure that we're interested in. But the building segmentation models that are in existence, or at least widely available, are trained on high quality labels in industrialized nations. So for a lot of African countries, you might have some high quality labels, but they might not be that many, or you might have a lot of labels, say from OpenStreetMaps or other open source data, but those labels might not be of very high quality. So how can we start to learn, but learn with lower quality data and still be able to make strong inferences? The other thing that's been brought up is just the quantity of data. Yes, that's a challenge here also. And to address that, we're thinking of ways to merge other data sets with what we have, either data sets on roads, data sets on buildings, data sets, survey, nighttime lights, different things to augment the performance that we are seeing. And the question is, where does that data reside, and is it available for the countries that one is interested in? Finally, as I mentioned at the beginning of this short talk, was that the goal is really to learn from places that have or that are more advanced in their electrification efforts and apply that to places that are now undertaking those mass electrification efforts. So we really have issues around transferability where things that might be quite prevalent in, say, East Africa might not be as prevalent in West Africa. For example, settlement patterns look very different just based off of agricultural practices. They look very different from East to West. So thinking about how do we develop robust models so that they're applicable to other countries. I think that's about it. Thank you.
That was really fantastic. Thanks, Simone. So everyone in the audience, feel free to drop questions into the chat. We have a couple from the moderator side, but I think there's a really quick one, Simone, for you. Just what type of satellite images did you use in your analysis?
Oh, sorry, I didn't mention. It is a digital globe, 50 cm resolution, what you would find like Google Maps.
Perfect. Cool. So I guess I have a first question for all of Simone, Bhekisipho, and Nathan. So you mentioned, various, general challenges for doing work in machine learning and energy systems in Africa, et cetera, and also some very specific applications. If somebody wants to actually start doing work, right, who would they work with? Who are the players in this space? And then generally speaking, like, how does this answer differ between the different African contexts in which you work as to who you would actually work with?
Okay, I'll start with it. I think currently in South Africa, obviously it's academia, because that's where all this the technical guys, that's where they are. So in terms of industry, they're lacking those kind of like skills. So it will be kind of like a waste of time going into them. But if you can target universities, that will be great. Then universities there. The good thing about universities, we've got advisory boards, so we can always interact with them to tell them as to the kind of work that could benefit them in terms of moving forward. So I'm sure some of you are aware that in South Africa, we've had huge problems regarding power, and our main kind of like service provider of power has been struggling of late regarding maintenance issues and stuff like that. So which surprisingly during the lockdown we have not had any load shedding compared to when there was load shedding before that. So you can imagine how machine learning could be utilized in that, in terms of dealing with load shedding issues. That will help a lot, but only academia can sort of like help here, the starting point.
Sure, I can jump in as well. Most of our partners are people that have data. Right. I mean, because we are academics, we can do the analysis, but we find a lot of our partners that do have data don't know what to do with it. Sort of coming back to what Bhekisipho said, and so they make good partners because they have the data, we have the skills, and so it's sort of ripe for partnership there. And there are still challenges in that. One, a lot of our partners spend a lot of resources collecting those data. They see them as very valuable. They're protective of those data. But in terms of who would be a good partner, I think that depends on what you're trying to do and what skills you're bringing to the table. As an academic, I'd say you need the people that have the data that you need. So we work with utilities, we work with off-grid companies. All of these organizations are collecting data at some scale. But the real challenge is, particularly with a large organization like utility, finding the right person to talk to is the biggest challenge. They don't always know within the organization where the data sits or who has it. And then building the trust over time to, allow that data to flow takes a lot of investment. And so find people with data. The challenge is it's not advertised where that data sits. So it takes an investment of time develop those relationships. So that's, yeah. But generally, I find people are enthusiastic to share data once they realize what the value proposition is for them. Right. So you need to approach it in a way that, you know, you're not just looking for their data, but you're doing something that's going to be valuable for them as well.
Fantastic. I'd like to ask you all, how do you feel like the machine learning techniques required for electricity applications differ depending upon location-specific factors? For example, how is the machine learning methodology itself that you see being applied in an African context different from that for a European context? In addition to there obviously being different stakeholders and data. And likewise, well, how do you see the methodological similarities between those different contexts?
I'd say that there are probably some considerations that may not necessarily occur in developed or industrialized economies. One of them I hinted at was just settlement patterns, where I'd say in at least the sub-Saharan African countries that I'm familiar with, settlement patterns really vary based off of what people use their land for. One is population density, also that might shift more people towards apartments versus you owning your actual house and then a shed outside your house. So I think that when machine learning models are being like developed for that context, there's a need to have those considerations. Unfortunately, those considerations are not explicit. Like you can't necessarily like sit on your laptop and know what they are. Yeah, so
Understood.
Yes. So, but I think those help to better tailor it to the needs, or help to better meet the needs that they're being developed for. Else, it might give you a result, but the question is how relevant is it to the context?
Absolutely, that makes sense. And it also makes sense that it's not the level of now use a 5-layer neural network instead of a 4-layer one.
And also, just to add on that, I think also you started with it, the data becomes critical. I mean, and each and every country or continent has got its own kind of like structures in place. So I always say there's no point using a system that's working in the US and try it in Africa without looking at the environment and also the resources and other stuff as well. You have to take that into consideration, which is the data issue always come into play. I'm surprised Nathan was saying Africa, it's easy with data. What we have in the Africa, there's always privacy issues regarding data. That's why our students, what they normally do, they are not giving data, local data, so they work with data from the US. When the student finishes his master's or PhD, he moves to the US because he's been working on a US related kind of like problem. So that's where Africa, that's where we're struggling right now. So if we could have access to data in the African context, students work on data in relation to Africa. They'll enjoy that because they're working on their own problem. You understand? Obviously, it's great to benchmark with the US or benchmark with the UK, but at the end of the day, you're working on an African problem with kind of like different kind of perspectives. So that's why.
Yeah, just to follow on the data issue, I mean, it's not easy to get the data. And I think that's the challenge, is that you have open source data in developed countries. Getting to the data in developing countries is a lot more challenging. Absolutely. But I think if you can demonstrate a value proposition to the data holder, then they're willing to share it. But it takes a whole lot more effort. You can't just go online and download it. We've invested years in building relationships with utilities and partners to access those data. So it's not as simple as just going online and downloading it, which is a huge challenge.
I want to mention very quickly in regards to what Simone said that we have a session later on at 4 p.m. UTC that has two experts on that will talk about exactly the thing you mentioned about settlements and remote sensing of settlements, and also experts who will talk about that in African context.
Awesome. Thank you for that, Constantine, and thank you, panelists, for your answers here. To combine two questions that we got from audience members, one asked about, can you transfer models that are learned, for example, in one East African country to another East African country? And similarly, can you, divide the data that you're using country-wise and subsequently apply models country-wise? So could you kind of address maybe the ways in which that would work, but maybe the ways in which that would break as well?
Actually, yeah, I mean, that's a good question. That's one of the things that we're considering, is how do models transfer between countries, East African countries, for example. To be able to do that, we've been working, I think Nathan mentioned this, we've been working on data from multiple East African countries. So it's not just the satellite imagery data that we have to obtain, it's also the electricity consumption data. So we've been working on the electricity consumption data from other East African countries so that we can test how transferable our models are. So I can't really give you an answer that they're very transferable or not very, but that's something that we're working on. And hopefully with the objective that we should find a way to make them transferable.
Yeah, and another challenge here is data standardization. And this is more, I suppose, in the off-grid sector where I do a lot of work, the data that different developers in different countries are collecting is sort of very different. And so building a model that is transferable is almost impossible because just the data that you're working with is not standard. And so creating that sort of standardization of data collection is something that organizations like AMDA, the African Mini-Grid Developers Association, is working on, for example, but we're not there yet.
Okay, awesome. Those are really great answers to all the questions. Thank you so much to all three of you for your participation. And I believe there's a way to clap if you are a participant. So if you'd like to press the clap button to thank our panelists, that would be fantastic.